All right, we're going to go ahead and move on to the fact here that's on our next page. And this relates this idea of spherical coordinates to the idea of triple integrals that we've been discussing. So here's what we have. Suppose that I have a solid that I can completely describe in that I can completely describe in spherical coordinates, okay? Such that maybe my theta has a range on it, my phi's got a range on it, and maybe my rho is actually bounded by functions. Now, if I meet these very special angle restrictions, just essentially making sure that I don't like retrace the same region more than once, like with the arm example we had in example 1 in the last video, we were able to see that if we spun all the way in a circle, like a full 360 degrees, we would start to create the shape of a cone. But if I spun like 5,000 degrees, I'm just going to keep retracing the same stuff. That's all these angle restrictions are really here to help with. Okay? But if it's the case that my functions there are continuous, they're non-negative for all possible values, I can go ahead and actually set this up here. A triple integral over that solid is ultimately going to look like, notice here, I still have my function, I still have the bounds on this phi and this theta, but you'll notice that those innermost bounds, which are the bounds on rho, they're functions, and I have this really awkward replacement here. You might remember that when we dealt with replacing dx dy with polar coordinates, we didn't just write dr d theta. We always had to write r dr d theta. And so we have something similar kind of happening here, where we have a rho squared sine phi d rho d phi d theta. It's not nearly as catchy, but it's what we have to work with. Okay. A couple things that are kind of interesting to take a look at here. One, since the bounds on the rho and the phi, or sorry, not the phi and the theta are just constants, they can be interchanged. You don't have to have the phi first and theta on the last, okay? You can reverse those. But in addition to this, this idea that we've seen in the past couple sections of dealing with projections is a little bit harder to work with here when we deal with this sort of spherical coordinate system. And so we're going to have to take a slightly different kind of approach to understanding how to set some things like this up. Fortunately here, example 2 is fairly intuitive, and we can take a look into see how we would evaluate something like this. Okay, so here's what we got. I want to evaluate triple integral over b of this terrifying looking function, dv. Okay, not too terrible. This is the region of B, though. It is all of the x comma y comma z points such that x squared plus y squared plus z squared is less than or equal to 1. Can you think about what that would look like? What is all the points where x squared plus y squared plus z squared is less than or equal to 1? Well, actually, again, that just turns out to be a nice sphere. That's the formula that we had for a sphere back at the beginning of the semester. So this is just a simple sphere. Now, if we wanted to think about trying to evaluate this and set it up as a nice triple integral, thinking about like floors and ceilings and different walls, that becomes a bit complicated, and we're going to get some really ugly bounds, really difficult things to integrate. It's not that it's impossible to do, but it's really not preferable. So if we were to go ahead and take a look here at how we might be able to work with this in spherical coordinates, we can make our lives easier. So I'll write this. I'll say in spherical coordinates, we can express B as, and I'm going to go ahead and write it again as a bunch of points with rhos, thetas, and phis. Okay, so I need to think about how I could imagine doing the same sort of thing we did in the last video, where I imagine my arm acting as kind of like that rho line, and where I would kind of need to rotate and look and spin and what distance I have to move to get all the points in this particular sphere. Well, let's again just imagine that we're standing like right at the origin. And maybe I'll start with the idea of rho. How far out do I need to move in each individual direction in order to guarantee that I get all points from the origin to the edge of the sphere? Well, yeah, that's actually pretty easy here because this would just be 0 to 1. I have to go 0 distance, or I have to walk all the way out to the edge, which is, since I have a sphere of radius 1, that would be 1. We could then think about the values of theta, which are also pretty simple here. Because if theta is going to say how far left, right do I spin, if I want to capture all the points, I need to spin completely around in a circle one time. I don't want to spin more because then I'm going to start retracing some stuff. And then the very last thing that I need to do here is consider that value of phi. Remember that phi is always going to start from 0. Well, sorry, I should rephrase. It's not always going to start from 0, but it must be thought of as starting from 0. And then I have to find values between 0 and pi. So I have to imagine starting with my arm facing or pointed straight up towards the ceiling. And then I have to think, how far down do I have to rotate in order to get all the points? And I think here I would have to rotate from 0 to pi. So this here represents the same exact sphere, but in spherical coordinates. Of course, since I'm working with a sphere in spherical coordinates, it should be super easy to work with. Just like working with a circle in polar coordinates is really easy, because that's kind of exactly what it's built for. So then here, when I set this up, my terrifying looking integral can be re-expressed in the following way. Again, I'm going to start with replacing all the stuff that I have in my function, so it's to be converted over. I want to replace x squared plus y squared plus z squared. And that's the same as rho squared, but now to the 3 halves. And remember, I also have to have that very unfortunate rho squared sine phi d rho d phi d theta. Yuck. And I can put my bounds on here. So it looks like my inner bounds are on rho, my next bound is phi, and my outer bounds are on my theta. If I was to take a look at evaluating this, I will work this one all the way through. I'm going to have an integral that looks like e to the rho cubed, rho squared, sine phi d rho d phi d theta. I could easily go ahead and think about how I could start to integrate this with rho. You might be able to see there's an easy substitution involved. I'm not even going to go ahead and write out the details of the substitution, but if you're interested in checking my work, I'm going to go ahead and use the substitution u is equal to rho to the third. That means I'm going to be left with here a 1/3 e to the rho third sine phi, evaluated from 0 to 1 d phi d theta. This is going to leave me with, let's see, 1/3 e sine phi minus 1/3 sine phi. Evaluating this isn't too bad. Oops, I forgot my other integral there. This is going to be, if I pull out all of my, if I pull out the sine of phi, I think I can re-express this as 0 to 2 pi negative cosine phi, and I would have 1/3, let me write this like this, 1/3 e minus 1/3. Got to evaluate that from 0 to pi. See, cosine of pi is going to end up as the value of -1. So I'm going to end up with 0 to 2 pi minus, at 0, I'm going to get the exact same thing. And when I integrate that with respect to theta, since that's just a constant, I'm just going to get 2 pi times all of that. It looks like I already have double that same quantity in there. So I think I'm going to end up with 4 pi 1/3 e minus 1/3. And ultimately, I would claim that that is then the final answer for that particular question. Okay, so this is the way that I could start to use spherical coordinates to work with this. Again, the evaluation is more of the cumbersome part. The part that's really important is understanding ultimately how can I get to this blue step that's right here? Because the evaluation after the fact is just number crunching. Understanding the setup is what's actually crucial. And we'll practice more of this setup in the next example.